Okay, so we have today, Wednesday, Friday. There is a lecture video and an online quiz for Wednesday. There will be an in-class quiz on Wednesday, probably an in-class quiz on Friday, and there's also a video and online quiz for Friday as well. And those are all posted right now. Just when you do the quiz for Wednesday, make sure it's the quiz for Wednesday. So then you don't have to come back and say, I did the quiz for Friday, and can you erase it and all that. Just make sure. That's usually why there's not more than one quiz at any one time. Also, there are some practice problems, questions for the final exam that are after the December 12th folder. There's an answer key for those, so there are some problems that you can review problems for the final exam as well. Your final exam is what, Monday? So there won't be much time in between. I'll post the answer key to the exam here probably tomorrow, even though I won't have the exam most likely done until Friday. It'll depend on how things go. But Friday at the absolute latest.
I just want to know if the final exam is all multiple choice.
The final exam is all multiple choice. It is totally comprehensive through what we talk about on Friday. So it's from the beginning to alkynes. And it's somewhat, evenly distributed amongst all the materials. So I don't know that there's an emphasis on one material or another, although certainly I would work backwards. Because at this point, a lot of the stuff at the beginning, Lewis, dot structures, resonance, may take some review, but hopefully it's not that intense.
Is it a departmental test?
It is not a departmental test. It's my final exam. So it's, I don't know, 90-ish multiple choice or matching questions. But it's my test. Next semester is the ACS standardized test, but this one is mine. Okay.
So this multiple choice will be like the ones that you've had on previous tests, or is it going to be more like 4 answers to 1 question?
Is it Scantron?
Oh yeah, it's Scantron. Yeah, it's Scantron. You make the Scantron your friend, it's your friend for life. Because if the last test I already had half of it graded, so that's why it went so quickly. There's also this little lab practical thing this week that's kind of got me a little bit occupied as well. But it's pretty much similar to it's similar to the types of questions that you've had, where in class problems, choose the major products, definitions, those kinds of things. So it probably is similar to what you've seen in the online quizzes, similar to that. But if you go through the problems that are at the end, I think that'll help. But it'll be RS, SN1, it'll be everything. So, all right, but that's we'll get closer to that on Friday. So what we have to do is we've got to finish up alkenes today. The sapling alkene chapter is due Friday. So, and there is a chapter on alkynes, but I'm not going to release that. I can't make it due, your guys' finals on Monday, so it doesn't do me any good to make it due like next week because your final's already over. There's supposed to be problems to help you prepare. So there will not be a chapter 9, so chapter 8/chapter sapling.
Can it be like optional?
Could it be optional? No. I could release it to give you access to it, but what I don't want is I don't want people doing, it's a comprehensive final, so it's not going to do you that much good to spend, a day doing nothing but alkyne problems. Unless you don't get alkyne problems, but I'd much rather you prepare for the final exam. So. Oh, yes.
Is there something that we can do if we have 3 exams on one day?
No.
Are you serious?
Yeah, I'm serious. That's in my syllabus. It's an urban myth that you can have one schedule just because you have 3 on one day. If you read the student handbook, it says clearly that missing a final exam is a serious matter. I believe that's the exact quote. But it says that, I don't have as much discretion if you miss the final exam as I do if you miss during normal, because that's my syllabus versus the university policy. And university policy is it has to be serious.
I think if I turn on the waterworks.
Not with me.
Okay, I'll go try my other 2 professors.
Sure, and maybe they haven't read the undergraduate bulletin.
Yeah.
But the undergraduate bulletin specifically says that 3 tests in one day is not an excuse. Because in theory, what you're supposed to do is when you schedule your classes, you're not supposed to schedule those situations. I know I'm an advisor. I don't think I've ever checked that for one of my advisees, but honestly, that's what they say.
I don't know if you said this or not yet, but what time is the exam?
It's okay, Dr. Nichols. I won't be.
Look in the syllabus. I think it's 1 o'clock. I think it's 1 o'clock that the exam is, but look in the syllabus.
Okay.
What was your question, Mary?
Nothing. I said I won't hate the player. I just hate the game.
It doesn't matter. I'm used to it. But yeah, three finals in one day is not sufficient. Okay, so alkenes, to finish these up, some of which we talked about last week. So the reactions that came after hydroboration oxidation were making epoxides. Then after making epoxides, we have to open them up. Right now we're only talking about acidic ring opening. And so the acidic ring opening means that your nucleophile, whatever that is going to add to the carbon that is most substituted. So it's like the bromonium ion. And so that was our acidic ring opening for the epoxide. Then we go to non-electrophilic additions. So up to this point, the reactions that we've been doing, and they ended at hydroboration oxidation for the test on Friday. So I'm going beyond that. The reactions that are non-electrophilic then may or may not be classified by Markovnikov's rule, but they would only be classified by Markovnikov's rule because there's an H, but there's no electrophile. So these are reactions that don't have an electrophilic mechanism. So to be honest, Markovnikov addition here isn't appropriate. So hydrogenation we talked about last Monday. Hydrogenation, you add 2 H's across the double bond. They add cis. Could it be regioselective? Absolutely not, because it's 2 hydrogens. So it's a symmetrical reagent. Could it be stereoselective? Yes, if you generate 2 chiral centers in your product, because this is 100% cis addition. So it could be stereo, but it's not regio. And so hydrogenation, you just add the 2 hydrogens, and then I showed you the little cartoon of the mechanism because the hydrogen sits on the surface of the metal, and then the alkene adds all at once. So it's a one-step process.
Dr. Nichols?
Yes.
Is that kind of like, what was the like, when they made ammonia, like easy to make for the first time? Didn't they use like a metal to?
What is it?
Is that kind of like this? No.
Fritz Haber.
I think so, yeah.
I don't know that I remember that off the top of my head. But catalysts, I mean, metal catalysts are used in in a lot of processes. So, yeah, the metal catalysts are, I think we have one other metal catalyzed reaction, but metal catalysts, particularly platinum and palladium with your precious metals, I mean, they're used for all sorts of things. Your muffler has a certain amount of precious metals in it so that, if you junk your car, they'll take the muffler out and recycle the catalytic converter stuff.
Yeah.
So, I mean, yeah, it's platinum, it's a bunch of things. Refineries have a lot of the precious metals as well. But in this case, the hydrogen sits on the surface. That may be the case for the Fritz Haber as well. That's what tends to happen is they sit on the surface and then induces that stereoselectivity. But you don't have to write that mechanism. Just recognize it's cis. So, new reaction, carbenes. So this one I skipped over last Monday. I'm not going to skip over it now. All right, so carbene additions involve adding a carbene to the double bond. What's a carbene? A carbene is a carbon with 2 electrons. It has no charge. Okay, so it's not a carbocation, it's not a carbanion, it's a neutral carbon that only has basically 2, 4, 6 electrons. But the carbon itself owns 4, so it's neutral. Has no charge. But obviously, because the carbene lacks an octet, it's very reactive. And so what will happen is that if you make a carbene, you can take this pair of electrons from the double bond and move it out to form a carbon-carbon single bond, then take this pair of electrons and form another carbon-carbon single bond, and what you end up making is a cyclopropane. So this is also sometimes called cyclopropanation. So I'm making a cyclopropane ring out of a double bond. So the question is, how do you make a carbene in order to make these cyclopropane rings? And there turns out there's 3 methods. There's diazomethane, there's a carbenoid, which is called Simmons-Smith reaction, and then there's alpha elimination. The first 2 make CH2s. So the diazomethane, basically diazomethane is CH2N2. Here are the 2 Lewis dot structures of diazomethane. Diazomethane is also used in another reaction we'll learn next semester. If you look at the second resonance structure, though, if you take and break this carbon bond and give the pair of electrons to the nitrogen, you're going to generate the carbon then, and the minus charge disappears because that was with the pair of electrons moving, and so you end up forming the carbon or the carbene. You also end up forming nitrogen gas. So this reaction is a little touchy in terms of my diazomethane itself has a gas molecule, nitrogen, embedded in it. And whenever you have molecules that have gas molecules that can easily form by just a movement of pairs of electrons, they tend to make great explosives. Because what happens is that your liquid or your solid then can generate a gas. There's a huge increase in volume, and usually there's heat to go with it. So then that volume expansion becomes even bigger because you're heating it. You're heating the gas. So whether it's your TNTs or your nitroglycerins and all sorts of things, they all tend to have gas molecules in them. So using diazomethane is a little tricky. So if you apply heat or ultraviolet light to this, you're going to form your carbene. You do that in the presence of double bond carbene adds. You end up with a cyclopropane ring. You can make a little bit more stable carbenes by using Simmons Smith, and it makes what's called a carbenoid. So if you take diiodomethane and react it with an alloy of zinc and copper, you end up actually making the carbene. But the carbene's pair of electrons is sort of shared by the metal, or the metal stabilizes it, so it's really easy, it's really stable as opposed to the standard carbene. So that's called a carbenoid when it's associated with the metal.
So it's zinc or copper you can use there?
Well, it's a zinc copper alloy.
Okay.
So it's both of them together.
Yeah.
But that makes the carbenoid. And then the third method is to take a molecule that has 3 halogens and 1 carbon and do alpha elimination. Now, we've never done alpha elimination. At least we've never done it. You may have done it not correctly. We've always done beta elimination. But alpha elimination would be if you lost an alpha carbon or lost something attached to that carbon. So if you take CHBr3, in lab next semester you'll talk about using chloroform, which is CHCl3. That's used as a solvent for spectroscopy like NMR. And if you take the equivalent, which would be called bromoform, and react it with KOH, the KOH will deprotonate the carbon. That will then give you the lone pair, give you C-, and then what will happen is the carbon-bromine bond breaks, you end up forming the Br-, and you end up forming the carbene, except in this case it's got 2 bromines. And you have to watch this reaction only from the standpoint of these kinds of solvents like chloroform and bromoform are really not base stable. And I've heard people say, oh, well, I'm just going to take the chloroform and I'm going to add a base to it. It's like, that's not going to end well, because your base is going to end up reacting with the solvent, making carbenes, and they're just going to run around the solution and do all sorts of things, if not explode.
What's the relative stability of the carbene with the bromines as opposed to the carbene with hydrogens? Is one more stable than the other?
I don't know that there's that big of a stability difference between putting hydrogens and bromines on there.
Okay.
It's just 2 different ways to make the carbenes.
Okay. Gotcha.
The third one's probably the easiest of the bunch, because you just take bromoform or chloroform and put KOH in it, and then hopefully there's something there for the carbenes to react with. In graduate school, we oftentimes we tried solvents, still do here, with things like sodium metal that react with the trace amounts of water in solvents. And somebody, I think, took the chloroform and added sodium metal to it. And if I remember correctly, the postdoc just looked at them and said, "It will explode." And I walked out of the lab. And the reason is because it was going to make all sorts of carbenes, and those were going to react, and it was going to get unnecessarily hot, and it just was not a good mixture. So we have to be careful with these halogenated solvents that we don't, particularly these kinds would have multiple halogens, we don't put basic molecules in them. But if I can make the carbene, then I can add it to the double bond. So if you think about epoxidation, where we added the oxygen to the double bond of the alkene, we said that was stereospecific, and we introduced the idea that a stereospecific reaction is one where if you change the stereochemistry of the reactant, it changes the stereochemistry of the product. And this reaction's no different. So if I took the trans alkene, which is at the bottom, the cis alkene at the top, and I reacted it with the CBr2, that carbene, I'm going to end up forming then in the top case the cis cyclopropane, and in the bottom case the trans. So changing the stereochemistry of the alkene changes the stereochemistry of the final cyclopropane. So this is stereospecific, just like epoxidation was. We only have 2 reactions that are we have 3 reactions that are stereospecific. This one, epoxidation, SN2.
Is there a reason the reactants are oriented the way they are, as opposed to like side to side or something?
I just put them that way so it was easier to see the cis and the trans. I think to make them fit too. If you want them horizontally, that's fine. There's no difference. So these are stereospecific reactions, but they're very unique. So if you see any of those 3 reagents before, it just means make cyclopropane. But again, this is a non-electrophilic addition. I'm not adding any electrophile, and the only term here that's relevant is stereospecific. Regioselectivity and stereoselectivity mean nothing in this reaction.
Does the BI sections, like, does it matter if you draw them with like a dotted or a wedge, like arrow?
They're actually, in that case, there's one this way and one that way. So one would get a bold, one would get a dashed. It doesn't matter. So that's forming cyclopropanes. So we talked about the hydroxylations, cis hydroxylations last week. The idea that you can add 2 OHs. Again, not going to be regioselective because it's 2 OHs, symmetrical reagent. But in this case, it's always cis, so it could be stereoselective. So if your major product has 2 chiral centers, because this reaction went 100% cis, and the 2 chiral centers, it would be stereoselective. So 2 reagents for this, KMNO4 base, and osmium tetroxide and hydrogen peroxide. So it could be, it can't be regioselective, could be stereoselective. I am going to just point out one thing here. And hydrogen peroxide has shown up a lot in the last few reactions. Now, before the exam, you could have made the argument that hydrogen peroxide, when it was present, always gave you anti-Markovnikov addition. Because before the test, it was HBr peroxide, anti-Markovnikov, and BH3 H2O2, anti-Markovnikov addition.
But not here.
Not from now on.
Okay.
Because hydrogen peroxide shows up in a lot of different reagents. So in this case, it's now with the OSO4. So it goes with that reagent. That will give you cis hydroxylation. KMNO4, why am I writing down there? KMNO4 and OH minus will add the 2 OHs. I am going to do a reaction with KMNO4 and acid, and it's not going to do that in a minute. So it's KMNO4 and OH adds 2 OHs. So this was cis. And we went through the idea that it was cis because your pair of electrons could move from the double bond to the oxygen, from the Mn double bond into the magnesium, from the Mn double bond O to the out to the carbon. So in that case, the manganese has gained 2 electrons. That's gain electrons reduction. So its manganese is reduced, and then the other species is oxidized, which means that it gained oxygen, which is our organic definition of oxidation. The manganese ends up as MnO2, manganese dioxide, which is a brown precipitate. Maybe I'll come back to that, the significance of that, or how you can use that in a minute. So what we also said last week was, this is cis. You form a 5-membered ring. Oxygen, carbon, oxygen, manganese, oxygen, carbon. It's forming a 5-membered ring. 5-membered rings are not big enough to stretch from the top of one double bond underneath to the bottom of the other end. So 5-membered rings, 4-membered rings, all have to add cis. Hydroboration was a 4-membered ring. This is a 5-membered ring. So that's why we get cis addition. And so then the base will come in, strip the manganese off, and leave you with the cis diol. Okay. So that's where we get the stereoselectivity, because it's 100% cis.
And we don't need to know how the manganese is stripped off.
No, we don't need to know that process. The manganese, that would be more in the area of inorganic
Okay.
or non-organic. As soon as we involve metals and stuff, it becomes not organic anymore. What reasonable, complicated metals like manganese. So it's cis because it forms a 5-membered ring. The osmium tetroxide does the same thing. The difference between the two is KMNO4 is cheap. It's the purple solution that you used like in General Chem to do titrations with. Osmium tetroxide is a little bit more expensive. It's a precious metal. And so in this case, while this reaction occurs and we end up having there are 2 oxygens that are missing, we end up forming that 5-membered ring. That 5-membered ring with the osmium is basically reacts with hydrogen peroxide, and the osmium goes back to OSO4. So in this reaction, what we do is we use a little bit of OSO4, a catalytic amount, and then lots of peroxide. And so what happens is that after the double bond has reacted, the OSO4 is regenerated, so it just keeps going on and on and on because of the cost. KMNO4, I dump in 1 mole equivalent because I don't care, it's cheap. But osmium is much more expensive. Either one of them give you 2 OHs, not Markovnikov or anti-Markovnikov, and cis. So that's, I think, the last of the additions where I'm adding 2 things. So the new additions are what? 2 H's, 2 OHs. I think that's it. Now, the last reaction isn't an addition, it's a cleavage. So the last series of reactions is called oxidative cleavage. Oxidation meaning I'm going to add oxygens to these molecules. Cleaving, I'm going to cleave the double bond. So there's a couple reagents that do this. They do it slightly differently. So let me explain how the reaction occurs, just in terms of writing the products. So when you do oxidative cleavage, you're going to cleave the double bond. So I'm going to write the molecules over here without the double bond present. I got it. There. So all I did was erase the double bond. Bless you. And at the bottom molecule, I would just erase the carbon-carbon double bond. So now the oxidative part means I'm going to add carbon-oxygen double bonds where the carbon-carbon double bond was. So each of the carbons that was involved in the double bond now gets a carbon-oxygen double bond. So that's where the oxidation or oxidative comes from. I've now added oxygens and I've cleaved it. For these molecules, I've gotten ketones and aldehydes. And before we talk about the specific reagents, we just need to talk about oxidizing carbonyls. Okay. So we'll come back to these molecules in a minute. But here's the oxidation pattern. So if you have a ketone and you want to oxidize it, You can't. Ketones will not accept any more oxygens. They will not undergo reaction with any kind of oxidizing reagents. Let's just say hydrogen peroxide, for instance. The ketone won't react with that. And the bracket O means just oxidative reagents that I'll list here in a minute. But aldehydes can. Aldehydes can be oxidized to carboxylic acids. Now, it's a relatively easy process. So that is oxidation because the molecule gained an oxygen. Went from CH to COH. There's some oxidation reagents that will oxidize aldehydes to carboxylic acids. Oxygen gas will over time. Peroxide will, KMNO4 will. The oxygen in particular, if you have really, really old bottles of aldehydes sitting around, a lot of time when you go to use them, they'll be half solid, half liquid. They're half solid because the aldehyde got oxidized to a carboxylic acid. Lots of hydrogen bonding, physical state then becomes a solid, stronger intermolecular forces. The liquid is typically the aldehyde. H2O2 will do that, and so will KMNO4. The reason I show you this is because if we go back to these cleavage reactions, if you make ketones, regardless of the reagent that you use, and I'll show you the reagents in a minute, ketones are stuck. They're done. Once you cleave the molecule, make a ketone, that's the final product. If you make an aldehyde, on the other hand, it's going to depend on what the reagent is. If the reagent involves peroxide or any oxidizing reagent, that aldehyde will be oxidized up to a carboxylic acid. Okay, so there are reagents that will do that. There are reagents that won't oxidize the aldehyde. But we're going to cleave, and then we're going to look at the molecule. So here's the three reagents that you could use to do cleavage. One is KMNO4 and acid. Okay, KMNO4 and hydroxide does what? Adds two OHs cis. KMNO4 and acid cleaves the double bond. I guess my suggestion is if you remember KMNO4 with OH adds OHs, that may help. It may not. You may have to be more creative than that, but that's the difference. Acidic cleaves. So it cleaves, and KMNO4 oxidizes aldehydes to carboxylic acids. So if you made an aldehyde, it will become a carboxylic acid. So when I say that it makes ketones and carboxylic acids, what I'm saying there is if you got ketones, they're untouched. If you make an aldehyde, it will get oxidized up to a carboxylic acid. There's also two ozone reactions. And ozone is down here. This is O3. That's the dangerous ozone. Ozone with peroxide will cleave. The peroxide will oxidize aldehydes to carboxylic acids. But if you react ozone with R2S, which is called a thioether, sulfur as an analog of oxygen forms the same kind of compound, so you can get an SH. That's called a thiol, and the ether equivalent, R2O versus R2S, that's called a thioether. So the thio term means sulfur, or zinc and HCl. So what happens is that when you react a double bond with ozone, you form this ozonide, and then that ozonide gets treated with either peroxide or R2S and zinc and HCl, and it basically breaks the double bond and it gives you your carbonyl compounds. So ozonolysis is the way to break the double bond. You get the same products that I showed you earlier. We'll go back to those products in a minute. So these are the three conditions. Two of them, aldehydes get oxidized. Only in the third, doesn't it? So ozone is good in the upper atmosphere, right? It keeps the UV rays from, giving us sunburn or skin cancer. I guess the severe form of sunburn that we would get if we didn't have the ozone layer in the upper atmosphere. Probably wouldn't have much life if from all the UV lights hitting us. Ground level ozone's bad. Right, in summertime in Cleveland, we get these ozone action days where you're not supposed to cut your grass or fill your car because the hydrocarbons get out in the atmosphere and they create ozone. Jet exhaust will do that. You sometimes see the brown streaks where the planes come in. That's partially ozone. All the car traffic downtown would give you that. LA's got ozone issues. Denver has ozone issues. There's ground level ozone is bad. It's a respiratory, causes respiratory issues because ozone's a reactive molecule and it will destroy things like double bonds, the insides of your lungs. So rubber things in particular, you get a lot of ozone if they're exposed to a lot of ozone. A rubber molecule is a long chain with single bonds and then double bonds. Well, if the double bonds start breaking, the chains start falling apart, things crack, things disintegrate. So, ground level ozone's bad because it is a reactive molecule. But in the upper atmosphere, perfectly fine, absorbing all the ultraviolet light and keeping us safe. But at the lower level, not so good. So when people want to complain about ozone, depends on where they're talking about it at. Just like if they're talking about chlorine. Chlorine gas, bad. Chlorine that's salt, maybe essential. So, going back to these problems then. So if we go back to these problems, if I had used ozone and let's say R2S, I would get ketone and then my aldehyde would stay as is. So those would be my two products if I used ozone and R2S. On the other hand, if I used ozone H2O2 or KMNO4 and H+, the ketone, nothing would happen to it. I get the ketone either way. But the aldehyde gets oxidized so that I would get that product and that product if I used KMNO4 and acid. Okay. So that's what I mean by ketones and aldehydes versus ketones and carboxylic acids. Down below, I have an aldehyde as well. So if I use ozone and R2S, I just get that product. If I use KMNO4 and acid, or if I use ozone and peroxide, this aldehyde part gets oxidized to a carboxylic acid. So what I showed you about splitting the molecule up, adding the carbonyl, then taking a look at what you get, that's going to depend on the reagent. So your final products are going to depend on what reagent you get. Those are the same two products. Now, the third combination that you can get for a double bond, because you can have one alkyl group attached, you can have two alkyl groups attached. One alkyl group will either give you an aldehyde or carboxylic acid. Two alkyl groups will give you a ketone. What happens if you have no alkyl groups? What would happen if I cleaved this molecule or this molecule? Well, just writing out products, I would get those two products for the top molecule. By again, just erase the double bond, put in carbonyls. And those would be the two initial products that I would get for the bottom cyclohexene. Now those would be the products that I've just written would be the final products if I used what set of reagents? What keeps the aldehydes as aldehydes?
Those ions,
Ozone along with the R2S or zinc and HCl. So if I used ozone and those two reagents, I would get the products as they stand. But what happens if I use CaMNO4, an acid? What happens to the ketones? Nothing. What happens to this aldehyde
becomes carboxylic acid
on both sides?
on both sides.
It becomes a carboxylic acid on both sides. So this product would be formed if I used like CaMNO4 and H+. So the one carbon aldehyde is called formaldehyde. Right? That's what dead stuff gets put in. Well, is that what that stuff gets put in? Is formaldehyde? All the stuff that's in the biology department floating around, it's dead. It's in formaldehyde. Actually, it's not. I think it's in methanol. I think they switched from formaldehyde about 12 years ago. But that's the one carbon aldehyde is formaldehyde. What's the acid called? No. You'd think so. Formic acid is HC double bond OH. So when there's two OHs on there, I've got H2CO3 is my acid. So this is H2CO3. What kind of acid is that? Carbonic acid. That's carbonic. H2SO4 is sulfuric. H3PO4 is phosphoric. H2CO3 is carbonic. Carbonic acid isn't very stable. It decomposes. Does anybody know what carbonic acid decomposes into?
H2O and CO2.
H2 and CO2 is what it decomposes to. Water and carbon dioxide. And if I had my carbonic acid with me, I would be sipping it now. But I forgot it. It would be Cherry Coke Zero, would be the one of choice. Carbonic acid's formed when you put carbon dioxide in water. So the fizzing is just, it's an equilibrium process. That's what you get when you oxidize a terminal double bond, a terminal alkene. And you may say, well, why would we want to break up double bonds? Normally we don't want to. Normally in organic we want to make molecules big. We don't want to destroy them and make them smaller. However, in the old days, when you had to determine the structures of molecules using non-spectroscopy, you're going to learn about spectroscopy next semester in lab. Things like infrared spectroscopy that tells you what functional group you have, NMR spectroscopy that can tell you the exact structures. Those have only been around since 1950. Before that, people had to actually use colorimetric tests to determine what their functional groups were. For instance, bromine's an orange liquid. If I add a drop of bromine to an alkene, what happens? Well, we know the bromine adds trans, but the orange color disappears. So if I add bromine liquid to a molecule, it disappears. That means it was either a double bond or a triple bond. If I take my KMNO4 and it reacts with the double bond, it cleaves it, and it forms MnO2, which is a brown precipitate. I know it's a double or a triple bond. Actually, I know more likely it's a double bond because a triple bonds, as you're going to find out for Friday, requires a little bit of heat to cleave the triple bond. So there are color tests that I can use to determine functional groups. And that's how things were done before spectroscopy, came about in the 50s. Markovnikov, Zaitsev, how did they figure out what their molecules were? I mean, that's a class all to itself on how they did that. Nowadays, I know in about 2 minutes if I have the right instrument. So one of the reasons why we would use ozonolysis sometimes is to break down a big molecule and then analyze each of the parts. And if we could analyze the smaller parts, then we could figure out what the bigger molecule is, because we know we had to cleave all the double bonds. If I cleaved a double bond and it fizzed, I'd know the double bond was at the end of the chain, because I'm cleaving the terminal double bond, it's forming CO2. So there's a lot of qualitative analysis that goes on with these organic molecules, most of which we won't talk about per se, but there was a time when you had to do that in the lab course. I had to do that when I was an undergrad. They gave us 4 test tubes of stuff and you had to figure out what they were. Yeah, that was the entire second half of the second semester. And it wasn't just 4 hours a week. It was like, go get the key to the lab from the secretary and try and figure out what was anytime you had free time. We don't do that anymore. We don't really do that part per se, but there was a time. So, cleavage is the last of the alkene reactions, but it is not the last of those reactions, because what you're going to find out for Friday is that you're going to need to do reactions on triple bonds. Now, before you do that, for Wednesday, it's going to be the standard stuff with a new functional group. How do you name it? Whatever. Alkynes are YNEs, so now we have pentyne, hexyne, etc. Wherever the triple bond is, there needs to be a number in front of it, so it's going to be relatively straightforward there. Although if you have a double and a triple bond, then is it an ine or an ene, depending upon whether the double bond or triple bond takes precedence. You'll find that out. Then how do you make triple bonds? So we've got to do some E2 reactions to get triple bonds. Then once you have the triple bonds, how do you react them? That's for Friday. Well, guess the reactions you use on triple bonds. All the same boring reactions as double bonds. HCl, HBr, H plus H2O, Br2, cleaving, all of that. So that's for Friday. So that's the last 2 lectures. And yes, we are covering 1 chapter in 2 days, but it won't seem that bad. Or it will, whatever. All right, in-class quiz on Wednesday. In-class quiz should be over the reactions we learned today.
You just gotta do it. It's like 1 page.